So if you think of designing a robot, we usually use a scale called the uncanny valley. And what it really tells you is your emotional response, or an emotional response of a person, with respect to what the robot looks like. So we go from completely machine-like, which are, these robotic arms that you see in manufacturing plants, to robotic dogs. And we can go all the way to humanoids over here. So if you think about the robot arm, how do you feel about it? Do you really have any emotions towards it? Very little, right? What about a robotic dog? A little bit more, right? It's kind of cute. Maybe the robotic cats have a little bit of fur, maybe cuter. Eventually you reach this peak. When there's a peak, there's always a valley, right? So there comes a point where your emotional response increases. But then you just have negative feelings towards the robot. We call this the walking corpse effect. So this happens for two reasons. One, the robot just may look very scary, and it has human-like capabilities, but you just don't like its appearance. Number two, you have high expectations of the robot because it looks human-like. So you expect it to understand what you're doing, what you're saying to it. You want it to do everything you've asked it to do, and it doesn't. So your feelings become more on the negative side because it's just not doing what you want it to do. And then eventually, you could get over to here. So usually we try to design robots here, such as Brian, where you still know it's a robot, you're not trying to be fooled, and you can understand what its capabilities are from the robot itself. So here we have kind of the main stages. So in order to interact with humans, we have to really consider how we interact with each other. So usually when you are engaged in an interaction, you may use facial expressions, speech, and gestures to convey your message. A robot needs to understand those and be able to display its own communication through facial expressions, speech, and gestures. Now this all has to happen in real time. So you say something or want the robot to do something, you don't have 5 minutes to wait until the robot responds. So you change your intent, the robot must understand that and change its behavior as a reaction to what you're doing. This is very difficult to kind of design, and we look back at human brains and see how humans can be able to do this and apply it to robots. As I mentioned before, we don't know too much about the human brain, but we know a few things. One main aspect of the human brain is we know we have a few layers in our brain. We have something called a reactive layer and a deliberative layer. So the reactive layer is, for example, you're walking down the street, you want to cross the street. It's a very busy street. You take a step down onto the street and a car comes out of nowhere. You react, you move back. You didn't think about it, there was no decision making at all. That's the reactive layer. The deliberative layer, on the other hand, is your decision making layer. All the decisions you make, what do I want for breakfast today, what am I going to wear to work, how am I going to get there, that's done through that layer. And then of course we have emotional modules, which are dependent on a lot of things, how our day's going, how our week's going, more long-term and short-term feelings. So we design a robot to encompass these layers of our brain as well. So Brian, for example, has the deliberative, the reactive layers, a robot emotional state, which determines its emotions. We also have designed it to have short-term and long-term memory, like we have. So long-term memory is what it needs to do. What's the objective of the robot? All the information is stored there. Information about the people it needs to interact with. And short-term memory is really based on, how's the robot feeling? What's its emotions at this state? And based on the interaction at hand, information from the reactive or the deliberative layer gets sent to be implemented by the robot for what you see. So I'm just going to show a video first of Brian. I'll let him introduce himself.
How is everyone doing today? Allow me to introduce myself. I am Brian, a non-contact, socially interactive robot developed in the Autonomous Systems and Biomechatronics lab at the University of Toronto. Let me give you a little background on myself. Non-contact means that I do not manipulate objects or physically come in contact with the person I am interacting with.
Okay, so that's a little bit, we'll see Brian in a few more slides and some more videos. So when we're looking at designing the robot, of course the brain matters, which is the output of what the robot is going to display and its behavior, and we need to think about how it's going to do that. So how will the robot, for example, display facial expressions? So again, the best way to look into that is to look at how we, as people, display facial expressions. So we have 22 muscles in our face. They come into two types, sphincter muscles, which are our 3D muscles that are around our mouths, for example, around our eyes, and then we have parallel muscles. These are the muscles that move in your cheeks and your chin and your forehead when you display different facial expressions. It's very hard to move only one muscle at a time. You have to be very well trained at it. So we move groups of muscles. So we can think of the robot doing the same thing. If we can group different muscles on the robot's face, move them together, we can actually display facial expressions. So we have designed Brian to have 12 muscles, 11 parallel muscles and one sphincter, the big one around the mouth, and some muscles that are distributed on the cheeks, forehead, and chin. I'm going to display a video, and Brian's going to show 3 facial expressions. See if you can guess which ones they are based on this muscle grouping. Any guesses to what that is? Happy? Do you see it smiling? The cheeks going up, the mouth, the corners going up. Okay, this is the next one. Can you guess what it is? Angry, yeah. So it's all in the in between the eyebrows, the inner eyebrows. And one last one. Sad? Droopy eyes? Some people say sleepy too. Yeah. So what we did was we took Brian, now we've designed this robot, let's see how people interact with it. This is the hardest part of designing these types of robots, is because people are not predictable, as we know, right? And different people have different personalities and different reactions to especially technology. So we did a few experiments. One of them is we just took the robot and we interacted with people where the robot was telling them kind of their activities of daily living. Like today you have a doctor's appointment, let's go for a walk, it's a nice day. And to see if people actually would comply with the robot. What would they say to the robot or do? So our examples were go for a walk, take your medication, go to the doctor's appointment, and the robot and the person just having a one-on-one interaction session. So here's an example of what the scenario looked like.
Hi, my name is Brian. How are you today?
I am fine, Brian. How are you?
I'm okay. Today is September 15th. Would you like to know your scheduled activities for the day?
Yes, please. Go ahead.
This morning you have a doctor's appointment. Don't forget to take your medication before you go. This afternoon your family is coming to visit you. Are you excited?
Of course I am. Is my granddaughter coming too?
Yes, I believe so. Is there anything else I can help you with today?
No, thank you. I think I am fine.
Okay then. Bye for now. I will come back and check on you later.
Okay, so you can see his stance towards the robot. And if you notice, the robot sways a little bit. Did you notice that? And of course, you saw from this angle, maybe hard, but the robot is waving to the person. The swaying is done on purpose. As we found, as people, we have personal space, right? And depending on our culture, that space could be very small or even larger. The robot also has personal space. So when we create this movement, it gives the illusion that the robot does actually have its own personal space, and people don't enter it. If the robot was standing still, no movement at all, people start poking through and looking at what's